Dear colleagues, welcome you to the next lecture on the theory of compilers. Today I'm going to go further with symbol parsers, and actually it includes two parsers. One is implemented by a backtracking algorithm, and other by following the lookout symbol and predict the grammar rules to be applied. And both of these algorithms is included in the class of top-down classes of derivation algorithms. So I'm going to specify the preconditions to be able to apply top-down parsing, and let's see how this algorithm works. The examples are from the textbook Compilers, Principal Techniques and Tools. So let's see the parsing by backtracking algorithm. As I mentioned, parsing means the generation of the sequence of derivation rules leading to the sequence of tokens by a certain grammar. In the case of backtracking algorithm, we focus on the first token first, and try to apply the derivation rules applicable for the initial symbol in the grammar, and we try all the derivation rules one by one. And if the derivation leads to a sequence which includes a terminal symbol, we have to match the terminal symbol with those symbols at the actual position, so the forthcoming symbols at the input. And if we fail, we try to apply another grammar rule. If the derivation leads to a non-terminal, we go further, call the same trial and error algorithm for the other non-terminal, and try the related derivation rules one by one. And if we cannot find any grammar rule which is applicable to the input, then we track back to the previous non-terminal and try another rule for that non-terminal. As an example, we are looking for a series of derivations leading to a type declaration which is similar to the type declaration is in Pascal-like languages. So we have a type which can be either a simple type or a pointer to an ID or an array. A simple type can be an integer, a character, or a number interval. And in the case of an array, we have to have the type of the elements and somehow the interval of the elements defined. And we are going to generate the sequence of derivation rules and the parse tree for the token sequence array bracket num dotted num bracket of integer. So at the input we have array first, and since type was listed as the star symbol identified by the non-terminal on the left-hand side of the first rule in the grammar, we are going to apply all the rules one by one for the type first. For the type, we have three rules. It can be either a simple or an upper row ID or an array. And that's why the first rule is type to simple. So first we have type here, and then simple is derivated from the type. And then, since simple is a non-terminal, we try to take into account all the rules applicable for the simple. So we are still at the initial token at the input, and try to apply the rules for the simple. The first rule is simple to integer, so we have the parse-tree like type to simple and simple to integer. And at this point, the integer does not match to the input where we have array, so we have to track back and try another rule. The next rule for the simple is simple to character. So we have a parse-tree like type to simple to character. However, at this point, the character does not match the array, so we try another rule for the simple, which is the last one, with num.not_num. Num.not_num is a series of three tokens. However, num does not match the array, and that's why we have to try another rule, but there is no other rule, so we have to track back in the recursion and try another rule for the type. So we eliminate the lower part of the tree, and we are going to check the forthcoming rule for the type. It starts with an upper row, and the upper row does not match the input token array. That's why we have to select another rule. And that, the next rule for type is array simple of type. So we extend the parse-tree with the symbols on the right hand side of this derivation rule, and here we have array as the first token in this right hand side, which matches with the symbol at the input. So we can go further and take a look at the bracket, which appears both in the parse-tree and in the at the input as well. So we can go further. Here we have a number at the input, and here we have a symbol in the parse-tree. Simple is a non-terminal, so we have to try to apply related derivation rules. The first rule is simple to integer, so we can place integer here, but integer does not match the number at the input, so we have to try another rule. And the next rule is simple to character, so we can place character here, but character does not match the number at the input, so we have to try another rule. And the next rule for the simple is num.num, so we place num.num here. Okay, and the number, the dot, and the number again are the same tokens what we have at the input, so we can match them and go further, and then go further and go further at the bracket and off as well. And finally we have integer at the input and type in the parse-tree. So at this point, since type is a non-terminal, we have to select appropriate derivation rule. and we try to apply type 2 simple rule first. So simple is placed in the parse tree, and the position in the input remains the same, so we try to derive integer here. And the first rule for simple is simple to integer, so we place integer here. And finally we have a parse tree where arrow simple of tie is applied to the type at the root of the tree, then num.num to the simple, and simple to the type at the end of the array definition, and integer to the simple here. So, and since this is the point where we can reach the end of the input sequence of tokens, the derivation is complete and we got the resultant parse tree. Okay, the next question is whether is it possible to estimate the next derivation rule without trying one by one all the derivation rules for a certain non-terminal. So we are going to take into account the so-called look-ahead, which is in the simplest case the single symbol from the input, so the forthcoming symbol from the input, so a single token. In more complex cases, the lookahead may include more than one tokens. And we are going to check whether looking at the next token from the input is enough information to guess what derivation rules to be applied. Let's see what sequence of tokens can be derived from certain non-terminals in our grammar. For example, if simple is derivated from the type, then the first non-terminal generated from simple can be either an integer, a character, or the first token from the sequence num.num, which is num. If a pointer is defined, we have an up arrow as the first symbol, and in the case of an array, the array is the first token. So if we take a look at this comparison, we can see that here we have three derivation rules for non-terminal type. However, the set of potentially generated first tokens are disjoint. So if integer, character, or num is at the beginning of the input, we have to apply the first rule, type the simple. If an upper row is at the beginning of the input, we have to apply type 2 upper row id, which is the second row. And if the input starts in an array, we have to apply the third rule, which is array simple of type. And let's note that predictive parsing is possible only if for any derivation rules with the same non-terminal on the left-hand side, the so-called first set denoting the first possible non-terminals generated from the left-hand side cannot have any intersection. So if the same non-terminal, same token can be generated from more than one grammar rules for the same non-terminal, then predictive parsing is not possible. How these kind of first sets can be defined? We will have a more precise formal definition, but just to have an impression on it, if the right-hand side of the grammar starts with a token, then the token is included in the first set. If there is a non-terminal on the right-hand side, then the first set of the non-terminal is included in the first set of the non-terminal on the left-hand side. And how such a predictive parser can be implemented. For example, if we assign a procedure for each non-terminal where the rules are selected according to the look-aheads and first sets, then we can construct a predictive parser. We have a function called match, which compares the certain token with that one on the input, and if the expected token does not match the one at the input, this function raises an error message. And as I mentioned, all the other procedures are assigned to the non-terminals. So we have a procedure for the type, and if we are going to implement the grammar rules for the type, we have to take into account the look-ahead, so the first symbol at the input. If this first symbol is either an integer, a character, or a num, then we are going to apply the rule type to simple in a way that we call the procedure assigned to the non-terminal simple. If the derivation rule contains a token, and we are going to match the input with the expected token. So for example, if the look ahead is an up arrow, we match the up arrow and then match the ID because it is expected according to rule type to up arrow ID that an up arrow and ID is at the beginning of the input. And as a third option, if the look ahead is an array, then we are going to match array and bracket and then call the simple to generate the sequence of tokens between the brackets and then the closing bracket and then match the off and finally call the type, which is practically this function, so recursively calls itself to generate the sequence of tokens for the remaining part of the input. And if none of the three options work, then we raise an error message because we only have these three derivation rules from the non-terminal type. In the case of simple, if the look ahead is an integer, there should be an integer, and the beginning of the input according to rule where integer is derived from simple, and for the simple to character rule we match character, and from simple to num.num rule, if the number is at the beginning of the input, we read num and num from the input, and if all these three cases fails, then we raise an error message since we have only these three options for the simple and nothing else. Okay, so a predictive parser can be implemented easily this way. However, it is important to note that this implementation hardwires the grammar itself into the code. So this kind of parser can only parse this grammar and nothing else. So it cannot be programmed, the grammar cannot be modified because it is hard-coded. Later on, we will learn a method where the grammar-related data will be added as an input to a parser, and it can be modified and extended before the syntax checking. And finally, let's see what are the necessary properties of grammars to be able to apply either predictive or backtracking algorithms for top-down parsing. In any case, left recursion should be eliminated, and for predictive parsing, not only left recursion but also the parts which are overlapping at the beginning of multiple rules for the same non-terminal should be eliminated. And finally, we have to somehow resolve ambiguity. Why do we need to eliminate left recursion? If you think of the implementation presented herein, if left recursion means that we call the same function assigned to the non-terminal in the same procedure, which is just which is under execution, it means that the procedure call itself and call itself and call itself and call itself and practically never stop, since during this call none of the symbols are read from the input, and the remaining number of symbols is the same at each step. In contrast, if we modify the grammar in a way that we place the repeated parts to the beginning and the closing parts to the beginning as well, then we do not have such a recursion where none of the inputs are read. So, for example, we have left recursive rules like here, where A calls A and A and A, and meanwhile alpha 1, alpha 2, and alpha 3 can be repeated. So these are the parts can be repeated multiple times. And finally, till alpha m. And finally, we place beta 1, beta 2, or beta n at the beginning of this sequence. So we can have an equivalent grammar leading to the same strings, which looks like here. So first we write the closing part, which is not repeated, beta 1, beta 2, beta n, and then continue with a new non-terminal A prime. And the A prime includes the part which where we can repeat the alphas either once, two times, or not at all. So A prime can be the empty string as well. However, it can generate a sequence of tokens where alpha 1, alpha 2, and so on, alpha m is repeated multiple times. However, in this case, this iteration is done in a way that first we have the sequence of tokens and then the non-terminal. So in this case, if this alpha includes at least one token, that token is read from the input, and since the input is finite, this recursive call will be finite as well. Left factoring means that if we have multiple rules starting with the same symbols, then this is concentrated to a single derivation rule where the remaining part after the similar input is expressed as another non-terminal A prime. So, for example, if we have like n rules for A, starting with subsequence alpha, then we specify a single rule to the A starting with alpha, and all the remaining part of the different derivation rules are listed for the A prime. This A prime may contain rules starting with the same symbols again, so sometimes these modification have to be repeated multiple times to get a grammar which does not contain more than one derivation rule starting with the same symbol. Okay, and the transition diagram is applied to identify whether the derivation is deterministic or not. If it is non-deterministic, then the grammar is typically not unambiguous, so it is ambiguous. And this state diagram graphically represents the same procedure that we have applied when we have created procedures for each non-terminals. So if we have multiple states and arcs between for each symbol, and this symbol is a terminal, we assume that this symbol can be read from the input, and if a symbol is a non-terminal, we go to the initial state of the state diagram related to that non-terminal, and going to the final state at that state diagram and return to the other end of the arc for which we had the non-terminal assigned. So for example, if we have a state diagram representing T and E prime, when we apply this step between these two states by E prime, it means that we have to reach the final state from the initial state of the E prime to step over this arc, which practically means that we have to either read a plus sign or read nothing, depending on the input. So if this kind of state diagram is visibly not deterministic, so we have multiple arcs with the same symbol to different states, then predictive parsing cannot be applied. And sometimes we can eliminate this non-terminism. However, if it cannot be eliminated, we cannot generate a predictive parser for the grammar. Okay, so during this presentation, I have introduced the backtracking algorithm, which is root first algorithm, tries all the grammar rules for any non-terminal. However, it can generate the parse tree. The only condition required is not to include left recursion in the grammar. However, I have presented that left recursion can be eliminated by the modification of the grammar and having another grammar producing the same sequence of tokens. And the disadvantage of the backtracking algorithm is that it often executes unnecessary steps, in contrast to the predictive parsers, which does not require trackbacks, but instead at each point it can predict the next derivation route applied from the actual known terminal and go further to generate the next token at the input. And finally, I have presented some techniques like elimination of direct left recursion and left factoring to prepare a grammar ready for top-down parsers, including the backtracking algorithm and predictive parser. And also, I have introduced the state diagrams, which can help identifying whether a certain grammar is appropriate to be processed by top-down parsers or not. Thank you for your attention.